Good morning, sir. Johanna arrived just on time. Professor Schmid will give the second lecture now. Last year,
okay, so let me look at X, which now will be a smooth complex projective variety. And then if one looks at the homology of complex coefficients, the fact that it has the structure gives us a decomposition. So with T plus Q adding up to K, and both of them are negative, although I won't write this down. And so this is the Hodge decomposition. And where does it come from? Well, the cohomology is calculated by the round complex. And if one has a differential form and writes it in terms of holomorphic and anti-holomorphic coordinates, then PQ means that you have P holomorphic differentials and Q anti-holomorphic differentials. But there is a slightly different point of view. Let me mention that. I mean, it's from the point of view of proof. It's exactly what I said, that the fact that it is projective, or more generally Kähler, means that any differential form can be, closed differential form can be written as a sum of closed forms of this type, modular exact forms. But let's say the cohomology of C, well, C as a sheaf, if one thinks in terms of the derived category, is also the holomorphic round complex. And the holomorphic round complex is filtered, and from that one gets a filtration of the cohomology. And since there is a real structure, one automatically gets two filtrations, and then those two filtrations determine the Hodge decomposition. Although the proof uses what I said before. Yes, and I should mention that this decomposition really by definition satisfies this complex conjugate condition. So, well, there is more structure. Namely, I want to look at S. Yes. So, I want to let N be the complex dimension. And then one has the intersection form. So that's the intersection form. But in terms of the ground complex, by measuring together forms and then integrating over the fundamental cycle, so it's not degenerate. And defined over 2, because it also can be defined in topological terms. And then I want to let C be the polarization. And what does that mean? Well, so it is a smooth projective variety, and when one says those words, what one means is that it can be embedded in some projective space. But so now let's let's pick a particular embedding. So X sits inside a projective space, and then take a hyperplane in the projective space, a generic one, and that will intersect X and something in codimension 2, and then by punctual duality, what one gets is a cohomology class, which is of type 1-1, and it's also defined when it's just regarded as a real cohomology class. It's also defined over Q. So, so this is a little awkward. I'm going to get this out. So then, in terms of these data, I can find L from HPQ to HQ plus 1, Q plus 1. This is cut product. Let's see. And lambda in the opposite direction. Minus 1, minus 1. At the adjoint of L, and I don't want to formally define it, but it's, there's a star operator, and lambda is star L star. So then it turns out that if one looks at the commutator, L lambda minus lambda L, this is equal to multiplication by n minus k on hk. And then it turns out that, yes, let me give a name to this operator, let me call it P. And then it turns out that if one calculates commutators, one gets these relations. And now again, this is a test, so you recognize them. Those, let's say the standard generators of the algebra SL2, say if one looks at these, they satisfy these commutation relations. And then one has so this is the Hodge decomposition, and then there is the second ingredient, which is the Latif decomposition. So H of the cohomology is equal to the direct sum for k going from 0 to n. So 2n is the real dimension, so n is the middle dimension. And then L from 0 to n minus k of L to the L applied to H, K, X, C sub prime, where the primitive cohomology yes, so here I use the index K, and actually it becomes more transparent if I use the index N minus K here. So Hn minus k xc sub prim. So since this index is less than or equal to the middle dimension, this will be a non-negative integer. This is the kernel plus 1 from Hn minus k to Hn plus k plus 2. So one gets this direct sum decomposition, and it is compatible with the Hodge decomposition in the sense that the primitive cohomology also has this direct sum decomposition according to Hodge type. And of course, L is of type 1,1, so in all of this, one has Hodge types, and so the compositions are completely compatible. And then in addition, one has the following so-called Hodge-Riemann relations. So if I look at I to the p minus q s L to the n minus k u v compact conjugate. This is, so I want to look at this for u in h p sub q x sub primitive and k equal to p plus q. Then I to the p minus q, this expression is, so u is in hpq and v is in hrs. Then this is 0 if pq is different from rs, and is positive definite if pq is equal to rs and q is equal to v. Or another way to say that is there is a Hermitian form with respect to which the Hodge decomposition is orthogonal. And then the sign of the form on the various Hodge pieces, since this is e to the p minus q, so when you increase p by 1, then q decreases by 1, and you have a change of sign by minus 1. So this form has alternating signs on successive pieces. So, and of course what I should point out is that so the primitive cohomology and its Hodge decomposition completely determines the Hodge decomposition. And it carries a Hermitian form. Well, let me say it very quickly. So, Hermitian form and the different Hodge pieces are perpendicular, but with alternating signs. So, this is, so if one takes all of this together, this is the so-called Hodge package. And what is actually curious is that in one place where all of this is described very efficiently and smoothly, well, maybe I shouldn't say efficiently, is Henri We's book, Variété Kählerienne. But in his account there is something very, very curious. Namely, he never tells you that these three operators span a copy of SL2. And so what he really does, without ever saying it, is he proves that finite dimensional representations of SL2 are completely reducible, and how you can write them down in the standard bases and what the linear forms do. So he does the representation theory of SL2 without ever telling you. And, well, very safe to assume that Huckleberry knew this. I mean, it's hard to imagine he did not. But then I would think it's remarkable that he fails to tell me. Alright, so this is the Hodge decomposition for the cohomology of a projective variety. And so now let me do this with parameters. So I want to look at V over T, P. So a family of smooth, polarized, complex projective varieties. Complex projective varieties parameterized by T, which is a complex manifold, or maybe typically it would be algebraic, but for the definition that does not matter. So what do I mean? So V is a complex manifold, P is holomorphic, projective of maximum rank, and for each T, if I look at the fiber over T, this is smooth complex projective and polarized. So what do I mean by polarized? So of course each fiber is polarized, but they're supposed to fit together. But I mean, the polarization is, for example, is integral, even though I didn't say that, applies in the cohomology, so it applies in lattice. So for the polarizations to hang together really means that they're locally constant. Okay, so what do we have here? In the C infinity category, this is modally apart. Now if you have the situation with a smooth suggested map of maximum rank, compact fibers, and closer is the product. And so what this means is that you get flat vector bundles let me call them HK prim. Flat vector bundles over T with fiber, the typical fiber, well, the homology to decay of V sub T, complex coefficients and primitives. So, in the C infinity category, this is a product. So locally all the fibers look the same. And this local trivialization is unique up to a continuous family, a differentiable family of diffeomorphisms of the fiber. But that does not act on trivially on the cohomology. So these bundles are flat. And so what do we have? So with a flat polarization class, C sub T, so for each T, one has C sub T, but it's flat in terms of the flat structure. And intersection pairing S for each T on the fiber, and C infinity subbundles H P Q sub T, namely H P Q T C sub primitive So let's see infinity, and we are in a holomorphic context. So, we hope that there's something holomorphic, but in the naive sense, this cannot be the case because when Q is not 0, there are anti-holomorphic pieces. So what one has to do is look at f sub t, p, which by definition is the direct sum of h L k minus L V sub t C primitive with L greater than or equal to P. So these are holomorphic. And if one looks at the derivative, so we have a flat connection, that means we have a flat bundle, so that means there's a flat connection. So this can be applied to any pattern vector. And so what happens when one applies differentiation of first order to Fp, well, if you look at how this was defined, then this is a decreasing filtration. So it's a decreasing filtration, and this ends up in Fp minus 1 sub t. So this is the next larger piece. Right? So when you differentiate once, then you spill over just one step. And this is called Griffith. This was first, maybe this saying was first studied by Griffiths, and this property is known as Griffiths transfer sum. So this is what one gets, and basically one should think of Fp as, well, the Fp encodes the Hodge decomposition because the primitive PQ cohomology is the intersection of Fp and Fq complex conjugate. So this determines the HPQ second. So it looks like less information, but it carries the entire information. And then, of course, one has the polarization condition that I to the P plus Q, P minus Q, S sub T satisfies those conditions. Okay, so that, what happens here is one looks not just at the Kähler package of Hodge, Lefschetz package of a single projective variety, but one looks at how it varies when the variety depends on parameter. That's what this formula says. And so why would one do that? Well, let's say the classical Toretti theorem for curves says that the Hodge decomposition completely determines the Riemann surface. So if you look at Riemann surfaces, well, there's a topological invariant, the genus, and then if you fix the genus, look at all projective curves of that genus, they are determined up to automorphism by the Hodge decomposition. And to call this a hope is an overstatement, but the idea was that, well, at least in certain cases, these Hodge decompositions should also determine what's called the moduli of the typical fiber, and that, as examples show, that is really expecting too much. But nonetheless, as one lets the parameter vary and sees how the Hodge decomposition varies, it does give some information about the geometry of the family. And so what I'm going to say next is going to be very vague. But let's say I, in the early 70s, and Kaplan Schmid in the 80s, these were very precise descriptions of the potential singularities of let's say the B of P sub T. And I mean, what does that mean? Well, if you look at families of this sort, let's say in the algebraic setting, so families of smooth projective varieties, almost always, if you look at any example, what you expect is that in this family, if you complete it, if you want the base space to be complete, okay, then almost always you will have some singular fibers. And so, of course, this picture does not extend to the singular fibers, at least not a priori. And so the question is, what happens to the Hodge decomposition as a typical generic smooth fiber degenerates into a singular fiber? And this was done in the case where the parameter space is one-dimensional, and that for a higher dimension. And of course, when you describe the singularities, then you are free to blow up, let's say, the completion of T along the singular locus, and so you can assume without essential loss of generality that in the one-dimensional case T is a punctured disk, and in the high-dimensional case it's a product of punctured disks. And so these papers describe the singularities of the Hodge flags quite precisely. And what is curious is that let's say, when this is a geometric family that completes geometrically, so if this gets embedded into a projective family with some singular fibers, then of course you might think that by looking at the family, you see, the geometric family of the singular fibers, how in the total family, the regular fiber degenerates into a singular fiber, then you should also see what happens to the Hodge flags and maybe get very precise information. But what is curious is that these geometric arguments, which were in fact done a few years later, they give you no more. So everything that you can try to say geometrically, and actually is more difficult, it's more bothersome to prove in the geometric setting, everything follows from these results, which do not assume that the family completes. So what this suggests, of course, is that when you have let's say a quasi-projective T, is that in some moral sense, even if the family is not given to you as something complete, in a moral sense, of course, there's some way in which you can complete it. So the limiting behavior of a Hodge structure looks as if, yes, it comes from geometry. And in some sense, it does. And so to prove what happens as the general fiber degenerates, well, one can do this by just looking at this abstract setting. So, yes, I mean, I should, and maybe what I said here is slightly premature. I mean, this statement premature in the lecture because what I should say.
Excuse me, just a general question. If T is quasi-projective, is V quasi-projective?
Well, I mean, you don't have to assume it to prove anything. Okay?
I don't know what that means.
Well, so actually, as I just said. I mean, the statement was slightly premature. And so you will see in a moment what the answer to your question is. Yes, so there is some level of abstraction. So first of all, suppose V is a finite dimensional complex vector space, and phi over Q. I mean, phi over Q simply means that there is a finite dimensional rational vector space, and this is its complexification. It's a extensive product of that rational vector space over Q with C. And then we suppose that S minus K is an integer, and S from V to the cross to C, a non-degenerate linear form of finality minus 1 to K, by which I mean that it's symmetric if K is even and skew if S is odd. So then a Hodge structure of weight K and B, polarized by S, is a decomposition of V equal the direct sum of V to Q, P and Q adding up to K, with V to P complex conjugate to V to Q, plus I to the P minus Q S of, well, I won't write it down, this is the previous condition. Namely that if I take I to the P minus Q S of E, this is then a Hermitian form, and the decomposition is orthogonal with respect to it, and it's positive definite, meaning that on VPQ, the sign changes as you know, in an alternating fashion. So this is an abstract polarized Hodge structure. Now, in the geometric case, P and Q are not negative. Here K can be negative, and then of course P and Q can be negative as well. But so that is the definition of an abstract polarized Hodge structure. And then suppose now we have, let's say, V over T, a flat vector bundle. With flat rational structure and flat bilinear form S, then one gets the notion of a polarized variation of Hodge structure. So I won't write down the formal definition because in some sense I did already. So instead of looking at the individual pieces, the PQ, you take a direct sum for, let's say, P greater than or equal to some particular P naught. Those things then have to vary holomorphically with respect to the base parameter, and again one has surface transversality. So Griffith's is then imposed as an axiom. And so then what we have over there is a particular case of one of these abstract variations of Hodge structure. And so, of course, the statements that I made about singularities, they can be proved, were proved, in this setting, even if it doesn't come from geometry, for arbitrary variations of Hodge structure. Right, so that, I think, that answers your question. So there's no reason for proof to assume the family of the original family is projected, justified as
But you didn't make any precise statements about the single force. No, you just said that.
there is a precise description.
Right.
And to tell you what that is, I would have to define the period map.
Yeah.
And then in terms of the period map, I mean, there's the so-called nilpotent orbit theorem, there's a two-orbit theorem, and they give you, what can I say? They give you very precise information.
So you're saying that this can now be done in this
This, well, in fact, not just can be, it was done that way. Right? I mean, the original proofs were in that setting. And then later, there were geometric proofs when the variation comes from family, a family where the family is completed. But you don't get any more information that way than you get by just assuming, just considering as an abstract variation of Hodge structure.
Okay, now I understand better what you meant with
Yes.
this.
Is that clear?
Yeah.
Okay, so now, so I cannot be completely explicit in what I'm saying next, what I'm going to say next, although I think it should be clear enough. Then there is a slight extension. One does not need to assume the existence of a rational or even real structure. Now, so in the definition of an abstract Hodge structure or a variation of Hodge structure, but let me warn you, of course, that one has to say things slightly differently, because here one has this decomposition, and then the S imposes these orthogonality and positivity conditions. So in this setting, instead of looking at the individual DPQs, one looks at the filtration. So so to get the translation from here to there, you don't look at the DPQs, but the filtration, namely taking FP, which is the direct sum of VL, K minus L for L greater than or equal to P. So the complex Hodge structure would be characterized by this filtration, and then the form S is part of what you need to make sense out of this, because then you get the second filtration by taking the orthogonal complement, by taking the orthogonal complements. And so then by having the flags, the S, you get the second filtration, and they're supposed to be related so that you then reconstruct the PPQ as the intersection of FP with the appropriate orthogonal complement. And then B should be the direct sum of these, and again you should have this condition. So to write this down will take longer than it's worth, but the point is that one can make sense out of this definition, a slight modification, without assuming that there's a rational structure. And then the same is true for the notion of a variation of Hodge structure. Again, one can say things, one has to say them somewhat differently, but one can say things without assuming that there's a rational structure. So that's going to be important for what I'm going to say later. So that means that one has the notion of a complex polarized Hodge structure, and the notion of a complex polarized variation of Hodge structure.
This is more general than the previous one.
Pardon?
This is more general.
Yes. Well, I mean, it's, let's say from the point of view of, one way to say it is that one can look at this slightly, at this setting, and then, you're free to say, suppose I have something like this, does there exist a rational structure for which S is defined over Q? And if there is, then fine, and it's really the old notion. So the new notion is, does not assume something which you can easily enough impose, and then you're back to the old situation. Does that make sense? Okay, so now, so before launching into this, I should say what's going to come next. So this is Psycho's notion of mixed point models. So suppose T is now smooth, quasi-projected, and then D, or at least that T, is the sheaf of linear differential operators on T with algebraic coefficients. And since we're in the algebraic setting, typically one would look at this in terms of the Zariski plot. Or sometimes there are reasons for saying, well, we can also do this in a complex category, complex homomorphic category. And so then the word D-model is short for sheaf of modules over the sheaf of algebras D, and usually required to be coherent over D, so that there should be, an image of at least locally of number of copies of D, and then with the finite number of relations. So then there are two important notions. Yes, first I should say, so these encode linear differential equations. And rather than making this precise, I'll give you a simple example in just a moment. So there are then two important notions, namely regular in terms of the corresponding system of differential equations means regular singletons. And holonomic So let me give you a simple example. So now T is C. So C is affine, and if one has, let's say, sheaves in the algebraics and sheaves over an affine variety, well, of an affine variety, to know the sheaf is the same as knowing its global sections. And so the global sections of D in this setting would be polynomials in Z and T by Z. Now, so polynomials, but of course these two quantities do not commute. They behave in the usual way. I mean, dz, the commutator is 1. And so the example I have in mind is take M, which is d mod d z by dz. So the system of differential equations that encodes is z df dz is f, or the solution is log z. And log z, the differential equation that gives you log z has regular singular points. And it is sufficiently determined. An example of something that is not sufficiently determined is that you look at functions of two variables, u and v, and you just say the f dv, the f by du is 0, but make no mention of what v does, and that's not sufficiently determined. Okay, so one has this notion, and so regular polynomial D-modules are closed under the standard operations of sheaf theory. At least on the level of the derived category. Namely, if F is an algebraic map, then F has direct image, inverse image, direct image with proper supports, inverse image with proper supports, and Garnier duality. So all of these can be defined in this setting. And then there is the Riemann-Hilbert correspondence from the bounded derived category of regular polynomial E-modules to the bounded derived category of constructible sheaves. So now it's constructible sheaves of complex vector spaces. So this is the Riemann-Hilbert correspondence, and it is an equivalence of categories. So RH stands for Riemann-Hilbert, and then, of course, this statement is to be understood in the following sense. On sheaves of vector spaces, at least at the derived level, one has these operations. This equivalence of categories relates the operations on this side to the corresponding operations on that side. Yeah.
Just a quick question here. Shouldn't one stress, or maybe I'm misunderstanding something, that these operations at the level of the model are not standard operations? You said standard operations of sheaf theory, but if I
No. I'm not. I didn't mean to imply that. I'm simply saying that when most of these operations are here, makes sense here.
Yes.
And there are operations which are related to it by this.
Exactly.
So I mean, the D-module operations you don't define in the same way.
Exactly, because I think that should be stressed.
Yeah. So unfortunately, I have to go back to the earlier notion of Hodge structure and variation of Hodge structure, well, Hodge structure at least. So in the setting of abstract Hodge structures, maybe complex. So in the complex setting, what does one have? One has a vector space V and the Hodge filtration. So since I allow the complex case, I'm not looking at the VPQ, but at the FP, and then there's the polarization form. So in this setting, a more general notion is mixed Hodge structure. It's a polarized mixed Hodge structure. Namely, two filtrations now, one has B, FP, and W sub K, and still in S. So where so first of all, as a general notational convention, if the index for filtration is at the top, that means decreasing. If it's at the bottom, it means increasing. So this now is increasing, and it's defined over Q when there is a rational structure. And then the condition is that the F dot induces a polarized Hodge structure of weight K on WK mod WK minus 1 for each K. So the mixed Hodge structure, as I say, there are these two filtrations, and on the level, so W is the weight filtration. And this is the Hodge filtration. And why would one look at that? Well, of course, the prototypical example is the cohomology on a smooth projective variety. And then I guess, what maybe I should have said earlier, is that this Hodge theory really took off in two directions. One was the direction of variation of Hodge structure, but at really the same time, the idea that if you have, let's say, a projective variety that is possibly singular, or more generally, a quasi-projective variety that is allowed to be singular, then the Lean produced not Hodge structures, I mean, you would not expect that, but mixed Hodge structures. Right? So mixed Hodge structures come up in the context of not necessarily complete and possibly singular varieties. Okay, so Now I can, there's one more ingredient of the story. So let's actually have T as before, and M a regular polynomial D module. Then a good filtration on M is a filtration so it may not start at index 0, so let me say it starts at index A, FA, M contained in FA plus 1, M contained in, and so forth, contained in M, and M is the union of the FP of M, and the filtration by O coherent O subnet. So O, I mean the Hodge functions, they are of course a subsheaf of D. So you can think of D as a sheaf of algebras over the sheaf of sheaf of fields in O. And but D, so a D module would generally not be coherent over O, because coherence means something like finite dimensional. And so that is not required. Although I mean the obvious D modules like just O, I mean O is a D module, and so O of course is coherent. But if you look at, let's say, D isn't, but let's take what the delta function at the origin generates when you apply D. That is not O coherent. So, so this is supposed to be a filtration by O coherent O submodules, such that when you apply D1, meaning differential operators of degree 1 or less to Fp of M, and this sits in inside Fp plus 1 of M, and this is equal for P sufficiently big. So that's the notion of a good filtration. And you notice that these filtrations are increasing before the Hodge filtrations were decreasing. But the reason is, the reason why they're increasing is because you could make them decreasing easily enough by defining F upper P to be F minus P at the bottom. But then the indices would be negative. So in the context of D modules, to get positive indices, one should make the filtration increasing. But one can always go back and forth between increasing and decreasing filtrations. It's just here to get negative integers, it's just better to make an increase. Does that make sense?
No, I find this confusing because if the filtration is infinite, what would be the decreasing filtration?
Well, you just go in the opposite direction.
Yeah, but I don't have.
So then you would have.
I don't have a place to start. I have nothing close with M, right? Because it's infinite.
No, I mean it just goes. I mean, so you can always go back. So F upper P, by definition, is F minus P. So if you choose negative integers, then you have an decreasing filtration. That's all. I So one can always go back and forth. I mean, just the general convention is increasing, and then one can go back and forth by this convention. All right, so, and now the important thing to say here is that the good filtrations in this context, regular harmonic exist, but are far from unique. And then secondly, the category of filtered regular harmonic modules. What would I mean by that? Well, by that, I would mean that you look at D modules together with specific with filtration. Yes? And so that's a category. Morphisms have to preserve filtrations. That's part of the condition. And so you can look at this category, but the problem is that it is not closed under standard functions. What I wrote before, I mean, F lower star, F upper star, you just can't define F lower star and F upper star in generality for general filtered D modules. Okay, so yeah, I have to go slightly over time to get I need another 10 minutes or so. So then cycle. So we construct a category, namely M of space. So this is mixed large models. So the objects are regular harmonic filter modules. So what I looked at here is statement 2, but of course not all of them, just some of them. With two filtrations. Well, I mean, filtered, of course, means I already have a filtration, I need filtration F. With a finite increasing filtration by regular harmonic Qaisar models of M, such that the F dot, F lower M, induces good filtrations on each WK, WK minus 1 of M, plus a rational structure on 1 of M, such that so now various requirements. another way of saying Riemann Hodge. Yes, thank you. Well, such that, first of all, so these are closed under the standard operations. So I won't repeat them. And again, of course, these are D-module operations now. I need to come back to what you said before. I mean, they're not defined the same way, but the ones that correspond to the standard operations under Riemann Hodge. So closed under the standard operations, it contains all polarized variations of Hodge structure. Because if you have a polarized variation of Hodge structure, you can look at the sheaf of holomorphic or algebraic sections of that flat bundle, and locally you have filtration. And so that is a good filtration, because the quotients are finite dimensional and the level of vector bundles finite dimensional vector. So the sections would be coherent overall. So when you have a variation of Hodge structure, then you do get a filtered D-module, and it's supposed to be in this category. And then 3, if you look at the category of mixed Hodge modules for the point, this is the category of polarized mixed Hodge. Yeah, so now there is quite a bit to be said. So first of all, how should one view this? So, yes, and then it is basically it's the smallest category that satisfies these conditions. So then that's a definition, which of course depends on the theorem that it exists. Okay.
Yeah, just thinking, trying to understand this.
Well, I will say, of course, more, then maybe you should ask the question later. Well, because I'm about to explain something. So how should one view this? So, because of this requirement, because of this statement, so if you have any of these D modules, you can go down to a point, and you get a polarized mixed Hodge structure. So what this does implicitly is, so this is now of course not a well-defined statement, nonetheless it's correct, is that this gives you mixed Hodge structures on just about anything where you have any reason to suspect that there is a mixed Hodge structure. And when there are mixed Hodge structures coming from geometric considerations, then it's not always obvious that they're the same ones, but in cases when it's been done, they are. So this is a perfectly general construction, and it really puts Hodge structures, mixed Hodge structures on anything where you have any right to expect this. Now, so this consists, the proof consists of a large number of papers, and they are horribly written. So, in paper 5, there may be a statement that, you use the results of paper 4, except that we now use this notation, that notation. They are almost impenetrable. And so this was proved in the, this goes back to the 80s, late 80s, early 90s. And I think to this day, there are some people who still have some doubt that there is actually complete proof. But, there is, many people, of course, do think that there is enough evidence of consistency that it's inconceivable that this is not correct. And then one thing which is relevant for where I'm going to end up is that, the arguments are very intricate, they are very tricky, but they are, for the most part, they are fairly formal. There are arguments with, which involve key modules, but there is one, let's say, basic analytic ingredient, and this is the description of the potential singularities of variations of Hodge structures. So that is the basic analytic ingredient. And so there are some attempts now to rewrite the story coherently, and then there is a different point of view, which I will describe now. So dispense with the rational structure. And so then the objects of the category of complex these Hodge modules on the space are filtered regular polynomial schema. And so there is no reason to look at the Riemann-Hilbert correspondence, because the Riemann-Hilbert correspondence, the only role it played was to make sense of the rational structure. And if I don't have a rational structure, then I can just erase it. Okay, and so what does this amount to then? So before I said if you look at filtered regular polynomial P modules, this is not a good category. Well, of course, this is a much smaller category. Namely, it contains complex variations of Hodge structures. It's closed under the standard operations. For a point, you get complex mixed Hodge structures. And it's the smallest category that satisfies all of it. So why should one care, and why should this be correct, or is it correct? So the reason one should care is that, of course, it's a more general statement. Right? Because when you do have a rational structure, that will be preserved by all the standard operations. So by dispensing with the rational structure, you're not really losing anything, because if there is a rational structure, just put it in. And then it makes sense of the category of filtered regular mononomial P modules. You just shouldn't look at all of them, just at the ones that you can generate by this procedure. And so then, why should this be, or why is it correct? So these so-called orbit theorems that I alluded to before, in the 70s and 80s, they were proved under the assumption that it's a rational structure. But then, almost immediately after the first paper came out, Delinian pointed out that you don't really need the rational structure. So the rational structure, what it means is that around, let's say, the visors, the monotomy has eigenvalues that are roots of 1. And if you forget about the rational structure, then all you have is that there are eigenvalues of absolute value 1. But that suffices. So, I mean, if you look at proofs, you have to just say, a few additional pages, and then this is true in that context. And since that is the basic analytic input, it's virtually certain that the result holds in this degree of generality. And in fact, there are some people now that are trying to write down details in that context. And so why is this relevant for my lectures? Is because I want to apply it in this context. So when I talk about representations, this is what we have. We don't have Russians, right? Of course, if one is really worried about the details, one can reduce it to the case that there is a rational structure, but that is an ugly artificial process. So it's much more natural to work in this context, and surely this is correct. But for our purpose, it's not absolutely necessary. But not to use it in this degree of generality would be really, really bad. Okay. Yeah, I'm sorry that I went over time, but
we were just talking to you on this is, I think, very interesting and very important for many of us. Maybe it would be an idea to start half an hour early tomorrow. And then you would have an opportunity to give 2 shorter lectures. Would that, you see that? It's too tired for you?
no, I think
Getting a little bit old, so
no, I think so this lecture had to be one lecture, right? I mean, or else to Zoom this.
No, but we could have a review tomorrow, because I wanted to ask a few questions, and if you don't mind, well, if it's not fair.
Well, I mean, I'd rather not make this 2 lectures tomorrow. Ask me some,
Not long,
ask me some questions tomorrow or right now.
Yeah,
So, very good suggestion.
Yeah.
So, are these categories abelian categories?
No.
What's the usual problem with filtered objects?
Oh, yeah. No, I mean, if you look at the arguments, it's, there are sometimes 4 or 5 filtrations, and they have to be compatible, and it's a zoo.
I wanted to ask you to review the definition there, because I was looking at it and I'm not sure I understand.
Maybe.
So, object, regular holonomic filtered models. Now, the word filtered there,
Means given equipped with a particular group filtration.
right, which means that then you can maybe cross it out, because on the next line it says with a finite.
No, those are
No.
Well, that's the
So
problem.
there is a second filtration.
Yeah, and I was not very clear how what the board says makes.
Finite increasing weight filtration.
Okay.
Sorry. I have some questions. Yes, sorry.
Because this was like a puzzle, what's with
Filtration W.
W, okay.
If you're Bourbois-Key, which fortunately I'm not, you would think that a filtered D module would be a D module filtered by D submodules.
No. Right.
In the first example, the first given, filtered D module.
No, so this, filtered in the context of D modules always means good filtration. And that's not the filtration by D modules. So the Hodge filtration is not the filtration by D modules. It's the filtration by O modules.
So there's some difficulty with English language.
No, in the context of D modules, when you say filter D module, you always mean.
Okay.
Right.
So
And in fact, the W is a filtration by D module.
So we could, so the F goes in the first line, so regular holonomic module with a good filtration F,
Yes.
right? With an additional filtration W,
Yes.
which is now a D module filtration.
Yes.
In the sense that. it's
And they're good as well.
Yeah, do we know finite, infinite W would?
No, that W is finite.
W is
The
finite.
weight filtration is always finite.
Okay, the
and
first
it
is
is defined over Q whenever there is a Q.
Right, the first is infinite a priori.
Well, sometimes it's finite, but
Right,
typically
a priori
it
is
is
infinite. induces good filtrations
On the
on
quotient.
each quotient of the other one.
Yes.
Okay.
Wait.
All right, yeah, okay, now it makes sense, but
So, I mean, you have-
said W there.
What you have now, I mean, there are several things I did not say, I mean, they're not necessary to make sense out of the statements. So, for example, I mean, what is very relevant in applications is that on the graded level, so I mean, the F induces filtration always on the graded level. But what you get on the graded level is the semi-simple.
Oh, as what?
That's a demon.
As a demon, semi-simple as a demon.
Semi-simple as a demon.
That's an assumption.
No, it's a theorem. I mean, that is part of the construction. It's part of the construction. So, I mean, I mean, it's not a theorem in the sense that, I mean, it's part of the construction.
Oh, and you didn't say, I agree, on what's the base variety on which this will be?
Any smooth quasi-projective variety.
Okay. So what are nice examples when X is not a point? Let's say on P1 or on
I gave you an example, right? So this was E by BZ.
That's right.
E by BZ. And so what is that? I mean, on C star, it's just O.
Right.
And at the origin, what you get is potential singular. I mean, you get the delta function, what's generated by the delta function by B.
Okay.
So you get negative parts. So that, I mean, when, and it clearly belongs to this category. And so the wave filtration means that at weight 0, you get just things that don't have singularities at the origin. And then weight 1 gives you the delta.
So the wave filtration on this thing is just 2.
Yes.
I see.
So and in
So
fact,
the D module is, so let's review this now. So the D module is as it was, it's just a D module. Then you say we have a clear enough good filtration on it.
yes,
Now we have to think about the second filtration, and that just has 2 terms.
yes.
That's what you're saying.
And the good filtration, of course, is simply by order of singularity.
Yeah.
I mean, negative power.
Okay. This help? So I just want to take more time.
Okay, so I guess we're not going to,
Well, no, if we could take
if we go over this.
Just one. So, does one ever do any kind of homological algebra in this category?
Well, I think
It's
the
not
proof,
really-
the proof is, how should I say, a very, very heavy dose of homological
It's
algebra.
some sort of non-abelian homological.
Yeah, no, people just look at some of his papers and,
Well, I'll take your word for it.
I mean, it will drive you to despair.
Where is he now, Saxon?
Well, he is at the University of Essen, at the University of Kyoto.
University.
So, I mean, it's a strange case. I mean, I think he is mathematically autistic. I mean, I don't think he's clinically autistic. He's mathematically autistic.
Interesting, yes.
I mean, you cannot ask him a question and expect a reasonable answer.
And it's not a language difficulty.
No, I mean, so, look, I mean, this is a major accomplishment. I mean, why isn't he at Rhodes?
I remember that this theory was used to give an alternate proof of the decomposition theorem.
Of course. Well, actually, what is perfectly clear, if you read his first paper, is what I'm going to do is to give a proof of the decomposition theorem that doesn't depend on finite characteristic going down to good. And of course, it's a more general statement of the decomposition theorem, of course. Especially if you don't require the rational structure. then of course you have a German decomposition theorem. But of course now there exists an even more general decomposition theorem, because you don't need weighted single.
I do prove that.
Which is a B.
Oh,
But hasn't the league cleaned up it?
No, I mean he has, to the extent one can say, from Valvin.
Which is validated, but I know that this is.
No, but they're not down there. Young people in Hodge theory
Who are
who are energetic and who say this is not a good state.
who are
Carlos Simpson.
Schneider, Christian Schneider.
because yeah, this is.
Okay, so